In the grand expanse of space, where galaxies stretch out like glittering islands in a cosmic ocean, a haunting question lingers. Is there a center to all of this? Does the universe, vast and enigmatic, have a focal point, a place from which everything sprang forth and around which all things revolve? Or is such a notion an illusion born from our limited vantage point? From ancient philosophers to modern cosmologists, the concept of a center has stirred the human imagination. Early civilizations gazed at the skies and imagined Earth at the core of existence, cradled by celestial spheres. This geocentric view, elegant and comforting, placed us at the heart of creation. Yet, as science peeled back layers of myth and misconception, Earth lost its central throne to the sun, and, eventually, even the sun was dethroned from any special position in the cosmos. Today, guided by Einstein's relativity and fueled by instruments like the Hubble Space Telescope and the Planck satellite, we now understand that the universe is expanding. Galaxies recede from each other, not because they're moving through space, but because space itself is stretching. But this revelation, as profound as it is, raises an even deeper mystery. If everything is expanding, then what is it expanding from? Could that origin point be the elusive center? Or is the very idea of a center meaningless in an infinite, boundless cosmos? This audio libro will take you on a journey through the theories and observations that attempt to answer this question. We will explore the Big Bang and the fabric of space-time, dissect the cosmic microwave background, examine the geometry of the universe, and even touch on parallel universes and the multiverse hypothesis. We will confront paradoxes, challenge our intuitions, and consider whether a center exists not in space, but in time, or perhaps only in perception. With each section, the narrative will flow seamlessly from one idea to the next, building a tapestry of cosmic understanding. The quest for the universe's center is, in truth, a quest for our place within it. So lay back, let your thoughts drift among the stars, and prepare to contemplate one of the deepest questions humanity has ever posed. The idea of a center is deeply embedded in human cognition. From the moment we begin to understand the world around us, we organize it around points of reference: home, our own body, the place we stand. It is only natural that early humans, looking up at the sky with awe and wonder, imagined themselves at the center of everything. After all, the stars rose and set, the sun moved across the sky, and the heavens turned above them. From this vantage point, the earth was not just home, it was the axis of the cosmos. Ancient civilizations such as the Babylonians and Egyptians developed cosmologies that placed Earth firmly at the heart of creation. But It was the Greek astronomer Claudius Ptolemy who crystallized this view into a detailed geocentric model. His universe, described in the Almagest, consisted of concentric spheres with Earth unmoving at the center, orbited by the moon, planets, and fixed stars. The model was mathematically complex, but it explained celestial motion well enough to persist for over 1,000 years. However, cracks in this worldview began to form during the Renaissance. In 1543, Nicolaus Copernicus published De Revolutibus Orbium Coelestium, arguing that the sun, not the earth, was the center of planetary motion. Though still imperfect, the heliocentric model initiated a profound shift. Galileo Galilei's observations through his telescope moons orbiting Jupiter, phases of Venus, provided direct evidence that not everything revolved around Earth. The Copernican revolution removed humanity from the physical center of the universe, and over the centuries, astronomy continued this trend of decentralization. The Milky Way was once thought to be the entire universe, with our sun at its center. Then came Edwin Hubble, who, in the 1920s, showed that the Milky Way is just one of countless galaxies, and that the universe is expanding. This discovery was seismic. Hubble observed that distant galaxies were redshifted. Their light stretched to longer wavelengths, syndicating that they were receding from us. More remarkably, this recession increased with distance, suggesting not motion through space, but an expansion of space itself. Every galaxy appeared to move away from every other, implying that there was no unique center to the expansion. To understand this idea, cosmologists often invoke the metaphor of a raisin-studded loaf of bread rising in the oven. Each raisin represents a galaxy. As the dough expands, all raisins move away from each other. Yet no single raisin is at the center of that expansion. The dough itself, representing space, grows uniformly in all directions. From the perspective of any raisin, it seems as though the others are fleeing, but no raisin is privileged. The universe, it seems, is centerless, but metaphors, while useful, have limits. The raisin bread analogy assumes the dough has a defined boundary and edge, that it's embedded in some external space, the oven. Is the universe like that? Does it expand into something else? Or is it all there is, with no edge, no center, and no outside? The modern cosmological principle holds that, on large scales, the universe is both homogeneous and isotropic. Looks the same in every direction and from every location. This principle underpins our models of cosmic evolution. If true, then every observer, regardless of location, would see galaxies receding from them, just as we do. In such a universe, asking for a center becomes like asking where the center of the surface of a balloon is. The surface has no special pointish curves on itself. In a higher dimension, in fact, if we imagine the universe as the three-dimensional analog of a two-dimensional balloon surface, we start to glimpse the subtlety of the question. In this view, our universe might be finite, yet unbounded. There would be no center in space, just as there's no center on the balloon's surface, only a continuous, self-contained geometry. But this balloon model also hints at a deeper issue. The expansion we observe is not into space, but of space itself. There is no surrounding void into which the universe grows. This is perhaps the most counterintuitive idea in cosmology, that space is not a stage upon which the universe plays out, but a dynamic participant in the cosmic drama. So where does that leave the notion of a center? If the universe is infinite and expanding everywhere equally, it has no center. If it's finite but unbounded like a hypersphere, it still lacks a privileged point. But if, on the other hand, the universe is finite and has a specific geometry or topology, could that define a central point? And what of the Big Bang? Isn't that the center? After all, it's the origin point of all matter, energy, and space. Shouldn't we be able to trace everything back to that moment, to that location? Here lies one of the greatest misconceptions. In cosmology, the Big Bang was not an explosion in space. It was an expansion of space. It didn't happen at a particular spot. It happened everywhere. Every region of the universe, no matter where you are, originated in the Big Bang. Thus, in a profound sense, every point in the universe could be seen as the center, because every point has shared in the same beginning. This idea challenges our deep-seated intuitions about space and time. It forces us to abandon the notion of absolute positions and embrace a more fluid, relative understanding of the cosmos. But the mystery doesn't end here. In the next section, we will dive into the implications of cosmic inflation and how it shaped the large-scale structure of the universe, perhaps providing clues about whether a central point might still make sense in some abstract mathematical sense. To understand whether the universe has a center, we must first examine one of the most pivotal theories in modern cosmology: cosmic inflation. This epochal idea reshaped our understanding of the early universe and its large-scale structure, introducing powerful, new concepts that challenge any lingering notion of a central origin point. Inflation refers to a brief period of exponential expansion that occurred a fraction of a second after the Big Bang, proposed in the early 1980s by physicist Alan Guth. The inflationary model posits that the universe expanded at speeds vastly exceeding the speed of light for an incredibly short duration, approximately 1036, 1036, 1036, 2103, 2103, 2 seconds after the Big Bang. During this epoch, regions of space that were once microscopically small ballooned to macroscopic scales. This sudden inflationary burst helps explain several deep puzzles in cosmology. One is the horizon problem, the question of why the universe appears so uniform in all directions. Distant regions of the cosmos are so far apart that, under standard expansion, they shouldn't have had time to communicate or exchange energy. Yet, the cosmic microwave background, CMB, the afterglow of the Big Bang displays a near uniform temperature across the entire sky. Inflation solves this by proposing that, before the rapid expansion, all regions of the observable universe were close enough to equilibrate. Then, inflation flung them apart, locking in the uniformity we now observe. But it also did something more subtle. It smoothed out any initial curvature or irregularities in the universe's shape, making it appear spatially flat and without a central peak or depression. This smoothness, born from inflation, complicates any effort to identify a center. If the universe looks the same everywhere, how could one point be privileged over another? In fact, one of inflation's chief virtues is that it predicts such homogeneity. It doesn't just obscure the notion of a center, it erases the very rationale for expecting one. However, inflation wasn't entirely featureless. It also seeded the tiny quantum fluctuations that later grew into galaxies, clusters, and filaments of matter. These fluctuations were stretched by inflation to cosmic scales and formed the basis of the cosmic web, the vast interconnected scaffolding of matter we observe today. Yet even this structure, as intricate as it is, lacks a central organizing point. The filaments extend outward in all directions, with no single node acting as a nucleus. Still, some theorists have wondered if inflation began at a particular location in a pre-existing space. Might that spot be considered the center? But this misinterprets the model. Inflation did not occur within space, it was the expansion of space itself. Every point in the universe experienced inflation equally. There was no edge, no predefined volume from which it spread outward. From the standpoint of general relativity and the field equations that govern inflation, the expansion was omnipresent. Here, a useful analogy comes into play. Imagine the surface of an inflating balloon again. Place tiny dots on the surface to represent matter. As you inflate the balloon, every dot moves away from every other, and none is more central than another. The surface is two-dimensional, but to our eyes, we perceive the expansion as happening into the third dimension. Now, translate that to a three-dimensional universe that may be expanding in four-dimensional space, or perhaps not in anything at all. In this analogy, the balloon's surface is the universe. It doesn't need a central point on the surface to expand. Some versions of inflation theory propose that the process might not be a one-time event. Instead, inflation could be eternal, generating a multiverse, a vast ensemble of bubble universes, each with its own laws and constants. In such scenarios, even if our own universe lacks a center, the multiverse might have its own internal geometry, potentially possessing a metastructure or origin point. Yet, these ideas remain speculative and currently untestable. Despite its success, inflation is not universally accepted as the final word. It makes predictions that are broadly consistent with observation, but it also raises new questions. What caused inflation? What ended it? Why did it occur with the properties it had? These mysteries hint that the story is incomplete, and perhaps further developments in quantum gravity or string theory will shed more light. But in the context of the question that drives this audiolibro in search of a center, inflation serves as a powerful argument against its existence. It renders the early universe uniform, scale invariant, and centraless. It also offers a cosmology in which all observers, no matter where they are, can consider themselves equally central. It decentralizes not just matter, but meaning. The concept of a center, after all, is inherently relative. It's tied to location, to structure, to asymmetry. But inflation produced a cosmos without those properties, at least initially. Over time, structure emerged from the seeds it planted, but no preferred point of origin was left behind. If anything, inflation democratized the cosmos, distributing its origins equally across every region of space. As we move forward, we must consider whether deeper physics, perhaps embedded in the very fabric of space-time, might hint at a hidden structure or topology that could resurrect the idea of a center, or perhaps the only true center of the universe is not spatial, but temporal. In the next section, we'll explore how time itself might serve as the organizing axis of the cosmos, and whether the birth of time can be equated with a kind of universal center. If the universe has no center in space, could it instead have a center in time? It's a curious thought, but not without merit. Perhaps what we often envision as a spatial center, the origin point of everything, is more accurately described as a moment, the Big Bang itself. Rather than imagining the universe exploding from a dot in space, we might imagine it emerging from a boundary in time, a singular moment when space, matter, and even time itself began. In modern cosmology, time is woven into the fabric of the universe. Thanks to Einstein's general theory of relativity, we understand that time and space are not separate entities, but parts of a single continuum spacetime. In this framework, the Big Bang is not a place in space, but a condition of spacetime. Every point in space today was once compressed into that singular state. And so, in a sense, the Big Bang occurred everywhere. This changes the notion of beginning profoundly. Rather than a fireball expanding into the void, the universe began as a hot, dense state in which the very fabric of spacetime was born. Time didn't exist before the Big Bang because there was no before to speak of. Just as there is no point south of the South Pole, the Big Bang is the starting coordinate of the temporal axis. We think of the universe like a cone stretching upward, with time as the vertical dimension and space spreading out horizontally. Then the Big Bang lies at the narrow tip of that cone. Everything expands away from it, not just spatially, but temporally. In this view, every galaxy, every cluster, every observer is moving outward in time from that singular moment. The center is not here or there. The center is then. This perspective also helps resolve the illusion that we, on Earth, are at the middle of everything. From our vantage point, it seems that galaxies are fleeing from us in all directions. The same would be true if we were located in a galaxy billions of light years away. The recession is not about us, but about the evolution of the entire space-time manifold. The center exists only in the sense that all of space shares a common temporal origin. One consequence of this idea is that, unlike a typical explosion, where fragments fly outward from a blast point, cosmic expansion occurs everywhere at once. No matter where you are in the universe, you are equidistant from that first moment. This implies a symmetry not around a spatial axis, but around the arrow of time. All of us humans, quasars, distant galaxies, drifting forward from the same beginning. But does this temporal center have any structure? Is there any sense in which it can be located or probed? According to the standard model of cosmology, we can look back in time by observing light that has taken billions of years to reach us. The farther we look, the older the light. Eventually, we reach a boundary. The cosmic microwave background radiation, or CMB. This is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe became transparent. The CMB offers a snapshot of the universe when it was young, hot, and filled with a glowing plasma. It is the closest we can come to seeing the temporal center. But even the CMB is not the beginning itself. To get closer, we must extrapolate with theoretical tools. As we wind the clock backward, we encounter denser and hotter states until we reach a point where our physics breaks down. This is the Planck epoch, named after Max Planck, occurring roughly 1043 seconds after the Big Bang. At that moment, quantum effects of gravity become dominant, and general relativity ceases to be a reliable guide. To understand what happens at or before that moment, we need a theory of quantum gravity, unification of general relativity, and quantum mechanics that remains one of the great goals of modern physics. The fact that time itself may have had a beginning places strong constraints on how we think about the universe's structure. If time began at the Big Bang, then the universe has a natural temporal center, even if its spatial extent is infinite. All timelines, all world lines, all causal paths radiate from that singular moment. In this sense, the Big Bang is the anchor point of existence. But what if time didn't have a beginning? Some cosmologists have proposed models where the universe existed eternally in a cyclical pattern of expansions and contractions. Others imagine a bound scenario where a previous universe collapsed and rebounded into our own. In these cases, the Big Bang is not a beginning, but a transition, a dramatic phase shift in a cosmic cycle. Still, even in such models, the Big Bang remains the most significant boundary we can observe or meaningfully discuss. It is the dividing line between knowable and unknowable, between the measured and the hypothesized. Whether or not it was truly the first moment, it serves as the closest thing we have to a temporal origin, and therefore to a kind of center, though not in the spatial sense our minds are used to. So, is time the key to locating the universe's center? Perhaps it may be that our very language misleads us. When we say center, we imagine a dot on a map. But the universe is not a static object. It is a dynamic, four-dimensional manifold, unfolding in both space and time. To ask where the center is may be to ask the wrong question. The real center may not be a position, but an event. Not a location, but a moment. In the next section, we will investigate how geometry, the curvature and shape of space itself, might offer another way to define centrality, or to prove that such a concept is meaningless. Does the shape of the universe permit a center, or does its geometry dissolve the idea entirely? To understand whether the universe has a center, we must examine not only its origin in time or the dynamics of its expansion, but also its geometry, its shape and curvature. Geometry in cosmology is not merely a mathematical abstraction. It is a description of how space behaves on the grandest scales imaginable. And depending on that shape, the idea of a central point might either emerge naturally or become irrelevant. Einstein's general theory of relativity tells us that mass and energy bend the fabric of space-time, curving it. On a trampoline causes the fabric to dip. A galaxy bends the surrounding space-time, influencing the motion of nearby objects. But when we scale up from planets and galaxies to the entire universe, we must ask, what is the overall curvature of the cosmos? Is it curved like a sphere, flat like a sheet, or hyperbolic like a saddle? Cosmologists classify the universe's geometry into three broad categories: closed, positive curvature, like the surface of a sphere. In this geometry, parallel lines eventually converge. And if you travel far enough in one direction, you could, in theory, return to your starting point. A closed universe is finite but unbounded. There is no edge, but there is a limited amount of space. Flat zero curvature, like a sheet of paper. Parallel lines remain parallel forever. A flat universe can be infinite or very large, but still finite in a special, non-repeating way. In this geometry, Euclidean rules apply. Open, negative. Curvature, like a saddle. Parallel lines diverge. This type of universe is infinite and expands forever, becoming more dilute over time. The geometry of the universe is determined by its densities, specifically the ratio of the actual density of matter and energy to a critical density defined by general relativity. If the universe's density is exactly equal to this critical value, the universe is flat. If it's higher, the universe is closed. If lower, it's open. So, what does observation tell us? Thanks to precise measurements from the cosmic microwave background radiation, especially those made by the WMAP and Planck missions, we know that the universe is remarkably close to flat. The deviations from perfect flatness are smaller than 0.4%, suggesting that on cosmic scales, the geometry of space follows the rules of Euclidean geometry. But here's the twist: even if the universe is flat, that doesn't mean it's infinite. It could be a finite flat universe with a toroidal topology, like a three-dimensional version of a video game, where traveling off one edge brings you back from the opposite side. In such a configuration, the universe loops around itself in a way that eliminates both edges and a center. This geometry carries profound implications for our question. If the universe is flat and infinite, it has no boundary, and by extension, no center. Every point in space is like every other. There is no privileged position. On the other hand, if it is closed, spherical, like the surface of a higher dimensional object, then space curves back on itself. But even in that case, there is no central point within the surface. The center exists only in a higher dimension we cannot access. Think of the surface of a balloon. It's curved and finite, but a creature living on it would find no central spot. The key here is that in intrinsic geometry, which is how space behaves for observers inside it, no center emerges naturally in a closed or flat universe. The center only appears if you can view the space from the outside, in a higher dimensional embedding space, which is not physically meaningful in general relativity. The laws of physics operate within the universe, not from some external vantage. Furthermore, the cosmological principle holds that the universe is homogeneous, the same in all places, and isotropic, the same in all directions on large scales. This principle is foundational to our models of cosmic evolution, and it's been supported by data. Galaxies are distributed roughly evenly, and the cosmic microwave background looks nearly identical no matter which direction we observe. In such a universe, not only is there no center, but there is no way to even define one. Still, some may wonder, what if the universe were open and infinite, or if it possessed a more complex topology? Could a special location exist, perhaps marked by some asymmetry, anomaly, or gravitational imprint? In theory, an asymmetric feature in the CMB, or a large scale, anisotropy in galaxy distribution could hint at a preferred direction or point. Some researchers have explored anomalies such as the so-called CMB cold spot or the axis of evil, patterns in the microwave background that seem to violate isotropy. These features have led to speculation about large-scale structure, cosmic defects, or even pre-Big Bang influences. But none of these observations have led to a definitive rejection of the cosmological principle, nor have they pinpointed any location as a central node in every consistent geometric model supported by data. The universe lacks a spatial center, and this isn't just a quirk of theory, it's a deep result of how space-time behaves under Einstein's equations. Space is not a static stage, it is dynamic, shaped by the matter and energy within it. In such a fluid, evolving arena, the concept of center loses its conventional meaning. But if geometry and curvature rule out a physical center, could there still be an observational central place that appears central due to the structure of light and time? In the next section, we'll delve into how our own location in space-time and the limits of how far we can see create the illusion of centrality. We'll explore the boundaries of the observable universe, the horizon of light, and what they really tell us about where we stand. When we look up at the night sky, we peer into a cosmic vault filled with ancient light that has taken billions of years to reach us. It is tempting to feel as though we are at the very center of something profound, surrounded in all directions by galaxies stars, and nebulae. The universe appears to stretch out evenly around us, no matter where we look. But is this impression real? Or is it a cosmic illusion shaped by the limits of our vision? To answer this, we must explore the concept of the observable universe. This is the region of the cosmos from which light has had enough time to reach us since the Big Bang, because light travels at a finite speed, about 299,792 kilometers per second. The universe has a finite age. There's a limit to how far we can see. That limit forms a spherical boundary around us, centered on Earth, called the cosmic horizon. Currently, the observable universe has a radius of about 46.5 billion light-years in all directions. Even though the universe itself is only 13.8 billion years old. This apparent paradox arises because space itself has been expanding during that time, stretching the distance that light has traveled. From our point of view, then, we are at the center of a vast sphere of visibility. But the same would be true for any other observer in the universe. A galaxy 5 billion light-years away from us would see its own sphere of 46.5 billion light-years centered on itself. This is a crucial distinction. The observable universe is not the universe. It is just our personal window into it. So, are we at the center? Technically, yes, but only of our observable universe. This center is not universal, but subjective. It's the consequence of our position in space-time and the way light travels. Every observer sees themselves as surrounded by the cosmos, simply because they can only see the part of it from which light has reached them. This relativity of observation is rooted in Einstein's theory of relativity. There is no preferred frame of reference in the universe, no special location, no cosmic landmark that designates a universal center. What matters is your location in space-time, your velocity, and your horizon of light. Interestingly, this also means that distant galaxies see us as we were in the past. A galaxy 10 billion light-years away does not see our current Milky Way, sees the Milky Way as it was 10 billion years ago. The farther out we look, the farther back in time we gaze. The cosmic horizon is both a boundary of space and a frontier of time. This raises a subtle yet profound question. Is there a real limit to the universe, or just a limit to what we can see? Most cosmologists believe the universe continues beyond our observable bubble. Perhaps not. But because we are limited by the speed of light and the age of the universe, we can never see beyond our cosmic horizon. The regions outside it are not necessarily unreachable in space, but unreachable in timelight from those areas has not had enough time to get here. In this way, our idea of a central position is deeply shaped by what we can observe, not by what truly exists. The universe may have no center, but our perceptual framework imposes one. We are always at the center of our light cone. Every observer is. This is not a feature of the universe itself, but of the geometry of observation. Some cosmologists use a more technical term, the past light cone. It refers to all the events in space-time from which light could have reached us by now. This cone narrows as we trace it back in time, converging toward the Big Bang. In diagrams, it resembles an hourglass, with the observer at the center of the top cone and the Big Bang at the point where it narrows. From this perspective, every observer's light cone intersects uniquely with the early universe, but none is privileged. Furthermore, the isotropy we see, the even distribution of galaxies and radiation, reinforces this principle. There is no obvious dipole structure in the cosmos that would hint at a real center. While small anisotropies exist in the cosmic microwave background, they are on the order of 1 part in 100,000, so minuscule that they don't disrupt the larger picture of uniformity. Yet, it's natural to ask, could the structure of the observable universe reveal hidden asymmetries? Could we detect a tilt, a bias, or a directional flow that might point us toward something central? Some have speculated about bulk flow, idea that large clusters of galaxies might move coherently in one direction. Initial reports of such a flow raised hopes that we might detect a cosmic asymmetry. However, subsequent studies have questioned these findings, and no consistent direction has emerged. As it stands, there's no compelling evidence that the observable universe is biased toward any one direction or location. In essence, the illusion of centrality is a byproduct of finite light speed, cosmic age, and relativistic symmetry. We see ourselves at the center, not because we are, but because light has simply had time to reach us from certain places and not others. The boundaries of our vision are not physical walls, but temporal horizons. In the next section, we'll confront the role of redshift, a key phenomenon in understanding how light stretches across space. By analyzing how wavelengths elongate as galaxies recede, we'll gain a clearer sense of how expansion shapes our observations and what it reveals about the underlying structure of space. Could redshift patterns hide clues about a center, or do they confirm its absence? Among the many strange and elegant features of the cosmos, perhaps none is as quietly revolutionary as the redshift. At first glance, it's simply a stretching of light, a change in wavelength. But in cosmology, redshift is more than a Doppler effect. It is a window into the past, a measure of expansion, and, potentially, a clue about the very structure of space. Let us begin with the basics. When an object emitting light moves away from an observer, the light it emits is stretched to longer wavelengths. This is analogous to the Doppler effect with sound. An ambulance siren lowers in pitch as it speeds away. In the case of light, this stretching shifts the color toward the red end of the visible spectrum, hence the name redshift. Astronomers use the symbol Z to denote redshift. A redshift of Z equals 1 means that the wavelength of the observed light has doubled since it was emitted. Higher redshifts correspond to more distant and, thus, older objects in the universe. The farther away a galaxy is, the more its light has been redshifted. But in an expanding universe, redshift is not merely caused by motion through space. It results from the expansion of space itself. As light travels through space, the very fabric of the cosmos stretches, and so too does the light. This is called cosmological redshift, and it reveals how the universe has grown over time. In the 1920s, Edwin Hubble observed that distant galaxies had greater redshifts than nearby ones. This discovery led to Hubble's law, which states that the velocity at which a galaxy recedes is proportional to its distance. The farther away a galaxy is, the faster it appears to be moving away from us. At first glance, this seems to suggest that we are at the center of the expansion. Everything is flying away from us. But this is an illusion, consequence of how expansion works. From any galaxy's point of view, all other galaxies appear to be receding. The pattern is uniform and isotropic. Every observer, no matter where they are, sees the same general trend. To visualize this, imagine inflating a balloon dotted with ink marks. As the balloon expands, every mark sees every other mark moving away. None of them is at the center of the expansion. The center lies in a higher dimension, outside the balloon's surface. In cosmology, there is no outside, just the balloon's surface. Growing everywhere at once, redshift is our primary tool for constructing the cosmic distance ladder. By measuring redshifts and associating them with known types of supernova and galaxies, astronomers can determine distances across the universe with remarkable accuracy. These measurements confirm that the universe's expansion is accelerating. Fact discovered in the late 1990s through observations of distant type Ia supernova. But what does redshift tell us about a center? Surprisingly little. The pattern of redshift is radial from every point. No matter where an observer is located, they will see galaxies redshifted in all directions, with the redshift increasing proportionally with distance. This symmetry makes it impossible to identify a privileged position. If the redshift were strongly directional or exhibited a dipole pattern, we might suspect an asymmetry in the expansion, a clue that could point to a central origin. But observations show no such pattern. The cosmic microwave background does show a slight dipole, and a Satra P1 side of the sky is slightly warmer than the other, but this is attributed to the motion of our galaxy through space, not to a universal asymmetry. Once that motion is subtracted, the CMB returns to its stunning isotropy. So, redshift confirms what other lines of evidence suggest, that the universe looks the same in all directions and from all locations on large scales. There is no special vantage point, no privileged origin. Redshift is a direct consequence of a uniformly expanding universe. Still, some cosmological models have explored whether redshift anomalies could hint at deeper structure. One example is the Lamater-Tolman-Bondi LTB model, which allows for a radially inhomogeneous universe. In such a model, the universe could be spherically symmetric but vary in density with distance from a central point. This would allow for the appearance of acceleration without invoking dark energy. If we happen to live near the center of a large void. But these models face serious challenges. Fine-tuning our position to an improbable degree would have to be extraordinarily close to the center of the void, which contradicts the Copernican principle, the idea that Earth does not occupy a special place in the cosmos. Furthermore, observations of the CMB, large-scale structure, and supernova distributions strongly favor the standard model with dark energy and a homogeneous, isotropic universe. Thus, redshift serves as a kind of cosmic equalizer. It allows us to map the universe's expansion history, but it does not privilege any one location. The more we learn from it, the clearer it becomes. The universe expands uniformly, and that uniformity undermines the idea of a physical center. Still, redshift also reveals a more subtle kind of structure cosmic time. It allows us to chart the history of the universe from the present moment back to the epoch of reionization, the Dark Ages, the cosmic microwave background, and eventually to the hot, dense origin we call the Big Bang. It shows that, while we may not be central in space, we are all traveling together through time. In the next section, we will dive deeper into this concept of cosmic time and how it provides a universal framework for understanding our place in the cosmos. Could time, not space, be the true coordinate that unites all observers, all histories, and all destinations? In a universe where space has no center and redshift offers no privileged vantage point, perhaps the deepest sense of orientation we possess comes not from where we are, but when we are. This leads us to a powerful concept in modern cosmology: Cosmic time. Unlike the time we experience in daily life measured by clocks, circadian rhythms, or planetary orbits, cosmic time is a global coordinate. It is defined as the time since the Big Bang, measured by a clock that ticks uniformly. For all observers who are at rest with respect to the overall expansion of the universe, these observers who move with the Hubble flow and are not influenced by local gravitational forces are considered to be in comoving frames. Cosmic time starts at 0, the moment of the Big Bang, and progresses uniformly for all comoving observers. This concept allows cosmologists to slice the universe into layers of simultaneity. What the universe looked like 1 billion years after the Big Bang, what it looked like 5 billion years after, and so on. Each slice is a moment in cosmic time shared universally across the cosmos, regardless of spatial location. This framework is immensely powerful. It allows us to speak coherently about events across the observable universe as having happened at the same time, even though the light from those events may reach us at different moments. For example, two galaxies on opposite sides of the sky might both have formed 10 billion years ago in cosmic time. Even if their light reaches us now from vastly different distances, in this view, time becomes the organizing axis of the universe. Rather than existing within a spatial structure with a fixed center, the cosmos exists as a four-dimensional manifold, evolving layer, moment by moment. Every point in space evolves in sync along this temporal gradient, like ink soaking evenly into a sheet of paper. Cosmic time redefines what we mean by now. Your now is not the same as the now of a distant galaxy because of the time it takes light to travel. But in cosmic time, both you and that distant galaxy exist on the same temporal layer. This shared structure provides a kind of unity that space alone does not offer. So, could we then think of the beginning of cosmic time, the Big Bang as the universal center? In many ways, yes. All of cosmic history unfolds outward from that temporal moment. Just as the rings of a tree mark the passage of time from a single origin point, the universe's structure is layered in epochs that radiate from the Big Bang. These epochs are not distances from a place, but durations from an event. In this sense, every point in the universe is equidistant from the beginning, not in space, but in time. All galaxies, stars, and observers are aging at the same cosmic rate, barring local relativistic effects. We are all on the same clock, sharing the same evolutionary timeline. This makes cosmic time a kind of temporal center, an anchor for all physical reality. Moreover, cosmic time allows us to trace the universe's development through clearly defined eras. the Planck epoch, the first 1043, 1043, 1043 seconds, where quantum gravity dominated, the grand unification epoch, where the strong and electroweak forces may have been one. Inflationary epoch, a fraction of a second of exponential expansion, reheating and baryogenesis, matter-antimatter asymmetry emerged. Photon epoch, radiation dominated the universe. Recombination and the CMB. At about 380,000 years, atoms formed, and the universe became transparent. Dark Ages, a long period before the first stars ignited. Reionization, light returned, and structure began to form. Stellar and galactic eras, stars, galaxies, and planets emerged. Accelerated expansion, the current era, dominated by dark energy. Each of these epochs is marked in cosmic time, not relative to any spatial location. The same eras occurred across the entire universe, wherever matter and energy evolved. This temporally unified framework allows cosmologists to simulate the universe's evolution on computers, to create models that match the distribution of galaxies we see, and to predict the future fate of the cosmos. It is arguably more fundamental than spatial coordinates, especially in a universe that defies spatial centrality. And yet, this structure doesn't fully satisfy the human longing for a place. We are spatial creatures. We crave position, location, orientation. But the universe seems to respond. Your position is no more special than any other. Only your time, your no unites you with the cosmos. Still, even cosmic time may have its limitations. Could there be something before cosmic time? Could the universe have had a prehistory, one that doesn't begin with t equals 0, but continues through it, perhaps in a bounce, a loop, or a higher dimensional origin? In the next section, we will explore speculative models that challenge the Big Bang as the beginning of everything. We'll examine cyclic universes, quantum bounces, and pre-Big Bang scenarios, and ask, if time itself had a prelude, does that undermine its claim to centrality? For most of modern cosmology, the Big Bang has served as the definitive beginning, the origin point of space, time, energy, and matter. But what if it wasn't the first act in the cosmic play? What if it was merely a scene change, one bounce in a long cycle, or a phase shift in a far greater and more complex multiversal structure? This possibility has intrigued physicists for decades, and it leads us into the realm of pre-Big Bang cosmologies. These models suggest that the Big Bang was not the absolute beginning of everything, but rather the beginning of our observable phase of the universe. If these ideas are true, then even cosmic time, so powerful and central in our current understanding, might not be truly absolute. And if time has no true beginning, then its 0 point is not a center, but just a marker. One of the most compelling alternatives is the idea of a cyclic universe. This is not a new idea. Ancient mythologies imagined time as a circle with creation and destruction recurring endlessly. In modern physics, the cyclic model has taken on new life through work by researchers like Paul Steinhardt and Neil Turok, who propose that our universe is one phase in a sequence of expansions and contractions. In these models, the universe undergoes Big Bang Big Crunch cycles, or perhaps transitions between brane collisions in higher dimensional space. Each cycle erases the memory of the one before, but the underlying structure persists. The arrow of time may continue forward within each cycle, but the cycles themselves are endless. In this picture, there is no central beginning, only repeating events like notes in an infinite melody. Then there are quantum bounce models, which arise from theories of loop quantum gravity. These suggest that instead of a singularity at the Big Bang, a point of infinite density and temperature, the universe reached a minimum size and then rebounded. The bounce replaced the singularity with a transition from a previous contracting phase into the current expanding one. If this is true, then our universe has a prehistory. A universe existed before the Big Bang collapsed and bounced into what we see today. In this framework, the Big Bang is no longer a beginning, but a bridge between eras. Cosmic time, in such models, might extend into negative values, ticking backward into a phase we cannot directly observe, but which left imprints in the structure of space-time. These ideas are speculative, of course. They are mathematically elegant, but hard to test. Yet, they offer profound implications. If the universe never truly began, then it cannot have a center in time. Just as infinite space has no middle, eternal time has no first moment. Some models go even further, suggesting that the Big Bang was a local event in a much larger multiverse. In eternal inflation, bubble universes constantly bought off from a background inflating space. Our universe is just one such bubble. Its Big Bang, a local event like a ripple in a vast ocean. If this picture is correct, then the center of our universe is not the origin of all that exists, but merely a point on an endless foam of cosmogenesis. Other theories inspired by string theory, like the ekpyrotic universe, envision our cosmos as a 3D brane floating in a higher dimensional space. The Big Bang was the result of our brain colliding with another. In this view, the true center of the universe might not even lie within our observable dimensions, but in the geometry and dynamics of the extra-dimensional realm. But is there any evidence for these speculative origins? There have been attempts to detect echoes from pre-Big Bang phases like certain patterns in the cosmic microwave background, CMB, or specific gravitational wave signatures. So far, no conclusive evidence has emerged. The CMB remains largely smooth, and no anomaly has yet demanded the abandonment of the standard model. Still, the allure remains. If we could one day detect a gravitational fingerprint from before the Big Bang, or find patterns in the CMB that defy inflationary expectations, we might gain access to this hidden history. The discovery would not only rewrite cosmology, would redefine what we mean by beginning, and whether the concept of a center in time has any meaning at all. And here lies the deeper philosophical question: does the universe need a beginning to be meaningful? If the cosmos has always existed in one form or another, then perhaps our search for a starting pointer, temporal center, is merely a projection of our own finite experience onto an infinite reality. In the next section, we'll shift focus from origins to structure. If there is no center in space or time, could there be one in the distribution of matter and energy? Could the large-scale arrangement of galaxies and cosmic voids hint at a subtle asymmetry, an organizing principle that defies randomness? From our small blue planet, it's easy to think of the universe as a chaotic sprawl of stars, galaxies, and dark matter. But when we zoom out far enough, beyond solar systems, past galaxies, beyond clusters, we begin to see a subtle but astonishing order, a cosmic web woven with filaments, nodes, and vast empty spaces. This is the large-scale structure of the universe, and it is among the most striking features of the cosmos. Could this structure, in all its complexity, contain a clue to some hidden center? Might the matter and energy of the universe be unevenly distributed in such a way that one region or region holds a special significance? Let's start with what we know. The large-scale structure of the universe is not random. Galaxies are not scattered like sand tossed into the wind. Instead, they are arranged in a web-like pattern. These structures enclose vast cosmic voids regions with far fewer galaxies than average. At the intersections of filaments lie galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies. When mapped in 3 dimensions using data from surveys like the Sloan Digital Sky Survey (SDS) and the 2DF Galaxy Redshift Survey, this web becomes apparent. The patterns are stunningly intricate, but they are also remarkably statistical. That is, while individual regions vary in density, the overall structure obeys consistent patterns and follows predictions made by cosmological simulations. These simulations begin with tiny quantum fluctuations in the early universe, slight over and under densities in the primordial plasma. As the universe expands, gravity pulls matter into the denser regions, forming galaxies and clusters, while the less dense regions evolve into voids. Over billions of years, this process creates the cosmic web. But, crucially, these fluctuations were random in origin. The seeds of structure were laid down by chance, and the universe evolved them through deterministic physics. The resulting web is rich and textured, but no part of it stands out as a central hub. There is no great attractor in the middle of it all. No supercluster that holds the entire structure in balance. Indeed, the largest structures in the universe, the Great Wall, the Hercules Corona Borealis Great Wall, the boat's void are immense. But none is centered on Earth, nor on any known cosmological coordinate. They are simply features in a vast, statistically homogeneous whole dot. To test the idea of large-scale centrality, astronomers use powerful mathematical tools. They perform statistical analyses of galaxy distributions, looking for anisotropies, clustering biases, or gradients in density that might hint at asymmetry. What they find is that, on scales larger than about 300 million light-years, the universe becomes statistically homogeneous. That is, no matter where you are, the average number of galaxies per unit volume is roughly the same. This observation is the backbone of the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. It's not a law of physics, but an assumption confirmed again and again by observation. And if it's true, it means that there can be no special place, no spatial origin, no central peak in the cosmic distribution of matter. Still, there are local anomalies, regions, of higher or lower density than average. Some have speculated that we may live near a relatively underdense region, which could mimic the effects of cosmic acceleration without requiring dark energy. But such hypotheses struggle to account for the full range of observations and require highly contrived positions for our galaxy, again violating the Copernican principle, which tells us not to assume we occupy a privileged place in the cosmos. And what about dark matter and dark energy? These elusive components dominate the universe's energy budget, making up around 95% of its total content. Their distributions, inferred from gravitational lensing, galaxy motions, and the CMB, appear to be uniform on large scales, while clumpy in detail. Dark matter follows the same web-like patterns as normal matter, and dark energy appears to be evenly spread throughout space. If these dominant forces do not coalesce into a central node or flow toward a preferred direction, it seems unlikely that any hidden centrality lies within their structure. There is, however, an emotional temptation to believe otherwise. We long for a cosmic map with an X marks the spot, for a center of the universe to orient our meaning. Yet, the universe denies us this simplicity. Instead, it presents a grand tapestry of structures complex, magnificent, but not hierarchical. It invites us to marvel at its patterns, but not to find ourselves at the heart of them. In the next section, we will explore how gravity, often thought of as the ultimate organizing force, contributes to this structure. Does gravity pull the universe toward a center, or does it merely shape local dynamics while respecting the deeper symmetry of space-time? Gravity is the architect of cosmic structure. It is the force that sculpts matter into stars, galaxies, and clusters, weaving the intricate cosmic web we observe today. Yet, despite its local power, gravity behaves quite differently when considered on the scale of the entire universe. In everyday experience, gravity pulls objects toward centers of mass. Apples fall to the ground. Planets orbit, stars and galaxies cluster around dense cores. It seems natural, then, to ask if gravity might also gather the cosmos around a single central pointive. There is some grand cosmic attractor that marks the universe's center. The answer, as modern cosmology reveals, is no. On the largest scales, the universe is expanding. This expansion is described by solutions to Einstein's equations, known as the Friedan-Lemaître-Robertson-Walker (FLRW) metrics, which assume homogeneity and isotropy. In this model, gravity acts to slow down expansion, but it cannot reverse or concentrate the entire cosmos into a center, especially when dark energy drives accelerated expansion. Gravity's pull is strongest where matter is densest, within galaxies, clusters, and superclusters. These regions act as local gravitational wells. Matter flows inward here, and cosmic structures form and evolve. But these wells are just tiny islands in the vast sea of expanding space. They do not define a universal center. Rather, they are scattered, discrete nodes within a largely uniform cosmos. Moreover, because space itself expands, galaxies beyond a certain distance recede faster than light. Not because they move through space, but because space itself stretches. This expansion creates horizons, regions beyond which gravity's influence cannot reach us. So even gravity's reach is limited by the universe's expansion. Interestingly, this interplay between expansion and gravity defines the large-scale fate of the universe. If matter density were high enough, gravity could halt and reverse expansion, leading to a big cruncha cosmic collapse back to a dense state. Such a scenario would naturally create a temporal center in the future, But even then, the spatial center remains elusive, embedded in a higher dimensional geometry. With the discovery of accelerated expansion in the late 1990s, driven by dark energy, the universe's future is expected to continue expanding forever. Gravity, once a force that might have gathered everything together, now faces an invisible, repulsive counterpart, pushing space apart on grand scales. This duality means that the universe's ultimate structure is one of dynamic balance. Gravity sculpts local matter into intricate structures, but the global expansion driven by dark energy ensures no single point can dominate as a center. In addition, Einstein's theory frames gravity not as a force acting within space, but as a manifestation of space-time curvature. This curvature is shaped by energy and momentum, but it obeys relativistic principles that forbid privileged positions. In other words, there is no center of gravitational influence at the universal scale, only varying gravitational potentials localized in space. Some speculative theories propose the existence of a great attractor region towards which many galaxies appear to be moving. This is a massive concentration of matter some 250 million light-years away, influencing local galaxy clusters. However, while the great attractor is significant locally, it is not a cosmic center. It is one node among many, a feature within the cosmic web rather than an origin point. In sum, gravity organizes the cosmos into islands of matter and energy, but it respects the underlying symmetry and homogeneity of space. It sculpts, it pulls, but it does not centralize. The universe expands everywhere, and gravity's domain is local, not universal. In the next section, we will consider how modern physics approaches the question of cosmic centrality through the lens of relativity and coordinate systems. How much of the idea of a center is dependent on the way we describe space and time, rather than on the universe's intrinsic nature. One of the most profound insights of modern physics comes from Einstein's theories of relativity. There is no absolute frame of reference. This means that notions of position, velocity, and even time depend on the observer's perspective. The idea of a universal center then becomes even more subtle, because it depends on the coordinates chosen to describe spacetime dot in everyday life. We use coordinate systems to specify locations, latitude and longitude on Earth, or the familiar Cartesian coordinates on a plane. But in cosmology, coordinates are more abstract, and different choices can drastically change how we interpret data. The Friedman, Lamater-Robertson-Walker FLRW metric is a coordinate system designed to describe a homogeneous, isotropic, expanding universe. It defines coordinates commoving with the cosmic expansion observers, moving with the Hubble flow, remain at fixed spatial coordinates as space expands around them. In this coordinate system, no observer occupies a privileged position. Every point is equivalent. However, one could choose other coordinate systems. For example, in the Lemaitre-Tolman-Bondy LTB models, coordinates can be centered on a specific point, which might be interpreted as a center of expansion or density. But such coordinate choices do not imply an intrinsic center in the universe. They simply reflect the chosen frame of reference. This is analogous to choosing the origin of a map. You can place the 0 point wherever you want. Whether you choose New York or Paris as the origin of a map doesn't change the geography of the Earth, only changes your description, because space-time is a four-dimensional manifold. Its geometry can be described in infinitely many coordinate systems. The absence of an absolute preferred frame means that any notion of a center is coordinate dependent. It depends on the vantage point of the observer and the mathematical framework they use. Furthermore, the cosmological principle implies that all commoving observers see the universe as isotropic and homogeneous. Therefore, the choice of commoving coordinates inherently removes any notion of centrality. Yet, humans instinctively search for centers and origins. We impose frames of reference because they simplify calculations and provide intuitive footholds in the vastness of space-time. But it's important to remember that these are tools, not fundamental features of the cosmos in general relativity. Physics is covariant. The laws hold true in all coordinate systems. No coordinate system is privileged. No center emerges universally from the equations. This coordinate freedom means that arguments for a cosmic center must be made carefully. A center that appears in one set of coordinates might vanish or transform in another. Thus, it is not a physical entity, but a feature of our description. In summary, relativity teaches us that the universe's structure and our place in it cannot be pinned down by absolute spatial coordinates. The idea of a center is, at best, a mathematical convenience, not an intrinsic property of the cosmos. In the next section, we will discuss how modern observations and experiments continue to test the universe's homogeneity and isotropy, reinforcing or challenging these principles. What do the data say about the universe's symmetry, and what might that imply for the notion of a center? The question of whether the universe has a center hinges critically on how well the cosmological principle holds true. This principle asserts that, on large scales, the universe is both homogeneous, the same everywhere, isotropic, the same in every direction. To test these assumptions, astronomers have developed a suite of powerful observational tools, One of the most important sources of data is the cosmic microwave background radiation, CMB. This faint afterglow of the Big Bang is remarkably uniform in temperature across the sky, differing by only about 1 part in 100,000. Such uniformity strongly supports isotropy. However, tiny fluctuations in the CMB encode information about the early universes. Density variations, the seeds of all cosmic structure. Detailed measurements from satellites such as COBE, WMAP, and Planck have confirmed this uniformity to extraordinary precision. The CMB shows no compelling signs of large-scale anisotropies that would point to a preferred center or direction. While some anomalies have been discussed, like the so-called cold spot or alignments dubbed the axis of evil, these remain statistically marginal and lack consensus as evidence against isotropy. Large-scale galaxy surveys also reinforce homogeneity. Projects like the Sloan Digital Sky Survey, SDS, have mapped millions of galaxies, revealing the cosmic web's intricate structure, but confirming that on scales beyond a few 100 million light-years, matter distribution averages out evenly. No large-scale gradients or asymmetries have been found that would imply a central hub. Furthermore, observations of distant type Ia supernova, used as standard candles to measure cosmic expansion, show consistent results regardless of direction. The acceleration of the universe appears uniform, supporting models without a special vantage point. However, astronomers continue to test these assumptions. New telescopes and surveys like the Dark Energy Survey Day, the upcoming Vera C. Rubin Observatory, and the Euclid mission will probe the cosmos with unprecedented detail. They may uncover subtle features that challenge our understanding or reveal hidden structure. If future data were to reveal definitive anisotropies or spatial gradients, it could force a re-evaluation of the cosmological principle and potentially hint at a cosmic center or edge. But as of now, the evidence overwhelmingly supports a universe with no preferred location. In light of these findings, the concept of a universal center loses its footing in empirical science. Instead, the universe's vastness and uniformity emphasize a profound egalitarianism. No point in space is special. No vantage is privileged. Yet, the search for understanding continues. Our instruments improve and our theories evolve. As we deepen our gaze into the cosmos, we confront questions that test the limits of observation, interpretation, and imagination. In the next section, we will reflect philosophically on what it means for humanity to live in a universe without a center, and how this perspective shapes our sense of place and purpose. The realization that the universe has no center is both liberating and humbling. For centuries, humans have sought a special place in the cosmos, a home at the heart of creation, a vantage point from which to understand the whole, to learn that space has no center, no privileged spot, reshapes this vision profoundly, philosophically. A center is often linked to meaning, purpose, and identity. To be at the center is to be important, unique, or foundational. The Copernican revolution began by dethroning Earth from the cosmic center, a blow to human ego that set the stage for modern science. Yet, the universe's lack of a spatial center invites us to reconsider what it means to belong. Instead of a fixed position, our place in the cosmos is defined by relationships, by the galaxies, stars, and particles that interact to form the tapestry of existence. We are participants in a vast, dynamic system, connected not by position, but by time, causality, and physical laws. This view fosters a sense of cosmic democracy. No point is privileged over another. Every observer in any galaxy sees the universe expanding away from them, surrounded by their own observable sphere. Meaning, then, is not found in centrality, but in the shared experience of being within the unfolding cosmic story. At the same time, the universe's immensity and apparent indifference can inspire existential reflection. If we are not at the center, what significance does that grant us? For many, the answer lies not in external validation, but in the ability to understand, to explore, and to create meaning ourselves. Science becomes a bridge between humanity and the cosmos, a means of connecting deeply to a universe that is vast, ancient, and often inscrutable. Our curiosity and capacity for wonder transform the absence of a center from a void into an invitation to seek knowledge, to find connection, and to embrace our place in a grand, boundless reality. In this light, the absence of a center need not diminish us. Rather, it challenges us to see ourselves as threads in the cosmic fabric, equal parts, observer and participant in the universe's ongoing narrative. In the next section, we will explore how the search for a center has influenced scientific thought and culture throughout history, tracing humanity's evolving relationship with this profound question. The question of whether the universe has a center has been a driving force in human thought for millennia. This quest reflects not only our desire to understand the cosmos, but also our yearning to define our place within it. Over time, this pursuit has woven itself deeply into the fabric of science, philosophy, and culture, shaping the trajectory of human knowledge and belief in ancient times. Many civilizations believed the Earth was the literal center of the universe. The geocentric model, famously developed by Claudius Ptolemy, placed Earth immobile at the center, with the sun, moon, stars, and planets revolving around it. This view was deeply intertwined with religious and philosophical ideas, asserting humanity's special status in creation. The geocentric worldview shaped not only astronomy, but the broader cultural understanding of existence. It reinforced a hierarchical cosmos with Earth and humanity at its apex. The heavens were perfect and unchanging. The Earth was the center of divine order. However, as observational techniques improved, cracks appeared in this model. Talos. Copernicus, in the 16th century, proposed a heliocentric model with the sun at the center, a radical shift that displaced Earth and humanity from cosmic centrality. His work laid the groundwork for a scientific revolution, challenging long-held assumptions. This upheaval was not merely scientific, but cultural and philosophical. The Copernican revolution questioned humanity's significance and the structure of reality itself. The universe was no longer a neatly ordered system with Earth at its heart, but a vast, dynamic expanse where no place held privileged status. Later, Galileo Galileo's telescopic observations supported heliocentrism, revealing moons orbiting Jupiter and the rough surface of the moon, contradicting the notion of celestial perfection. His advocacy for this new view clashed with prevailing religious authorities, marking a pivotal moment in the conflict between science and dogma. In the centuries that followed, the universe grew even larger in human understanding. The discovery of distant galaxies by Edwin Hubble in the 1920s shattered the notion that the Milky Way was the entire cosmos. The expanding universe suggested that there was no fixed center in space, reinforcing the Copernican principle on a grander scale. Simultaneously, the rise of relativity and modern cosmology revolutionized concepts of space and time, dissolving ideas of absolute position or universal center. Space itself became dynamic, curved, and expansive, not a static stage. Yet, the search for a center continued in subtle ways. Some scientists and philosophers sought special frames of reference, hoping to find a point of absolute rest or origin. Others embraced the idea that the universe was centerless, an infinite and homogeneous expanse in culture. The idea of a cosmic center persists metaphorically and spiritually. Many traditions hold beliefs about sacred places, the axis mundi, or cosmic centers that connect heaven and earth. These symbols reflect deep human needs to anchor meaning and identity today. The scientific consensus leans heavily toward a universe without a spatial center, yet the philosophical and emotional resonance of centrality remains. It shapes our narratives, art, and worldview Understanding this history enriches our appreciation of the profound journey humanity has undertaken from believing ourselves at the universe's heart to embracing our place as observers within a boundless cosmos. In the next section, we will examine how modern physics continues to grapple with the universe's origins, structure, and possible centers through cutting-edge theories like quantum gravity and string theory. Modern physics stands at the frontier of our understanding of the universe's deepest nature. As experimental observations have solidified the picture of an expanding, homogeneous, and isotropic cosmos, theoretical physics has pushed beyond classical frameworks to explore realms where space, time, and matter intertwine in unprecedented ways. The quest to understand whether the universe has a center continues to inspire new ideas, often arising from attempts to unify gravity with quantum mechanics. Two of the most promising approaches in this quest are quantum gravity and string theory. Both frameworks attempt to reconcile Einstein's general relativity, which describes gravity and the structure of space-time on large scales, with the principles of quantum mechanics that govern the very small. In doing so, they reshape our concepts of space, time, and origin. Quantum gravity posits that at the smallest scales, the order of the Planck length space-time itself is quantized. Instead of a smooth continuum, space and time may be composed of discrete atoms or networks, fluctuating in complex patterns. These models suggest that the classical notion of a single, well-defined center may break down at these scales, replaced by probabilistic, dynamic structures. One approach, loop quantum gravity (LQG), proposes that spacetime is a network of finite loops woven into an evolving spin foam. In this picture, the universe's beginning, the Big Bang, singularities replaced by a bounce from a previous contracting phase, avoiding infinities and singular points. This removes the classical idea of a unique spatial or temporal center and replaces it with a cyclic or emergent origin. On the other hand, string theory envisions the fundamental constituents of reality as tiny vibrating strings existing in multiple dimensions beyond the familiar three of space and one of time. These extra dimensions, often compactified at incredibly small scales, allow for rich variety of geometric and topological possibilities. The universe, in string theory, could be one of many brane worlds embedded in higher dimensional space. In some string-theoretic models, the Big Bang results from the collision of brane's higher dimensional membranes, leading to a birth of a new universe within a larger multiverse. In this framework, our universe's center might not exist within the familiar four-dimensional space-time, but could reside in the geometry of higher dimensions, inaccessible to to direct observation. Furthermore, these theories often predict a multiverse, a vast collection of universes, each with potentially different physical laws and constants. If this is true, then our universe is but one bubble in a frothy, cosmic ocean. This plurality challenges any notion of a single, absolute center of all existence. The mathematical richness of quantum gravity and string theory complicates the simple idea of centrality. Space and time become emergent phenomena arising from deeper, non-spatial and non-temporal quantum states. The center of the universe, then, if it exists at all, is not a point in space or a moment in time, but an abstract feature of underlying physics. Testing these ideas remains challenging. Experiments probing the Planck scale are beyond current technology. Indirect evidence, such as signatures in the cosmic microwave background or gravitational waves, is actively sought but not yet definitive. In the meantime, these cutting-edge theories expand our conceptual horizons. They invite us to think beyond classical intuitions about space, time, and centers, pushing us toward a more nuanced and profound understanding of the cosmos. In the next section, we will discuss the role of dark energy and dark matter, the mysterious substances composing most of the universe's mass energy, and their implications for cosmic structure and centrality. Dark matter and dark energy are among the greatest mysteries of modern cosmology. Together, they compose approximately 95% of the universe's total mass energy content. Yet, their true nature remains elusive. Understanding these components is essential for grasping how the cosmos is structured and whether a center might exist. Dark matter was first hypothesized to explain unexpected gravitational effects. Galaxies rotate faster than visible matter alone would allow, and clusters of galaxies exhibit gravitational lensing, bending light from distant objects in ways that imply far more mass than can be observed. This invisible mass, called dark matter, does not emit or absorb light, but exerts gravitational influence. Its distribution plays a crucial role in the formation of cosmic structures. Dark matter forms vast halos around galaxies and clusters, providing the gravitational scaffolding for normal matter to coalesce. The cosmic web, the vast network of filaments and voids, is shaped in large part by dark matter's invisible framework. Despite this, dark matter's distribution appears statistically uniform on the largest scales, mirroring the overall homogeneity and isotropy of the universe. No evidence suggests dark matter concentrates around a central point or defines a cosmic center. Instead, it permeates space broadly, shaping structure but not centralizing it. Even more mysterious is dark energy, a form of energy with repulsive, gravitational effects that drives the accelerated expansion of the universe. Discovered through observations of distant supernova in the late 1990s. Dark energy challenges previous assumptions that gravity would slow cosmic expansion. Dark energy's properties suggest it is uniformly spread throughout space with a nearly constant density. This smooth distribution contributes to the universe's large-scale uniformity. It acts like an intrinsic property of space itself, pushing galaxies apart on the grandest scales. The presence of dark energy implies a cosmic future of continued, accelerated expansion, further diluting matter and preventing any gravitational collapse into a universal center. Gravity's local organizing power is overwhelmed by dark energy's repulsive effect at vast distances. Together, dark matter and dark energy paint a picture of a universe that is both structured and uniform, dynamic and uncentered. The invisible mass scaffolds galaxies, while the invisible energy expands space everywhere evenly. This duality reinforces the cosmological principle and the idea that no point in space holds a privileged position. The universe has no spatial center toward which matter flows or from which expansion radiates. Instead, expansion occurs uniformly everywhere, and matter clusters locally within an overall homogeneous cosmos. Current and future experiments like the Large Hadron Collider, dark matter detectors, and advanced space telescopes seek to illuminate the nature of these dark components. Their discoveries could reshape our understanding of cosmic structure and evolution. In the next section, we will delve into how the concept of the observable universe frames our perspective on cosmic centrality. How does our finite horizon affect the idea of a center, and what limits does it impose on our knowledge? Our view of the cosmos is inevitably limited by the observable universe, the region of space from which light has had time to reach us since the Big Bang. This finite horizon imposes profound constraints on what we can know, and by extension, how we conceive the universe's structure and any notion of a center. The observable universe forms a sphere centered on the observer, in this case, Earth, or, more precisely, our location in space-time. It extends roughly 46 billion light-years in every direction, encompassing all matter and energy visible to current telescopes and instruments, because light travels at a finite speed. Looking farther into space is also looking back in time. Distant galaxies appear as they were billions of years ago, allowing us to reconstruct cosmic history layer by layer. However, this also means that every observer anywhere else in the universe has their own observable universe centered on their location. This leads to an intriguing consequence. Every observer perceives themselves at the center of their observable universe. No point is privileged, and the observable universe is a subjective sphere defined by light travel time and cosmic expansion. The idea that we, at the center of the universe, is, therefore, an artifact of observation, not a physical reality. It is similar to standing in a fog. No matter where you stand, the visible foggy sphere surrounds you, making you the center of your local view. This realization aligns perfectly with the Copernican principle, which states that Earth is not in a central, specially favored position in the cosmos. Instead, all locations in the universe have an equal claim to being central in their own observable spheres. Moreover, the observable universe is only a small fraction of the entire cosmos. Beyond the horizon lies potentially infinite space that we cannot see or influence. This unseen expanse might contain structures, phenomena, or even other universes beyond our comprehension. This limits our ability to identify any universal center, because we have no access to the totality of existence. The universe's global geometry and topology remain subjects of active research and speculation. Some cosmological models propose a finite but unbounded universe, like the surface of a sphere, but in higher dimensions, where traveling far enough in one direction returns you to your starting point. In such models, no edge or center exists in the traditional sense. Others consider infinite universes, extending endlessly with uniform properties. Here, centrality is a meaningless concept. There is always more universe beyond any point. Therefore, the observable universe's finite nature and the subjective centrality of each observer's horizon reveal that the concept of a cosmic center is deeply tied to perspective and limits of observation. This understanding challenges us to think beyond intuitive notions of place and to embrace a universe where position is relative. Horizons are personal and center is a shifting concept. In the next section, we will examine the role of cosmic microwave background anisotropies and what subtle variations in the oldest
light
tell us about possible deviations from perfect uniformity and the idea of a center. The cosmic microwave background CMB is the oldest light we can observe a faint afterglow from about 380,000 years after the Big Bang, when the universe became transparent to radiation. The CMB is a near-perfect black-body radiation field, remarkably uniform across the sky, supporting the idea of a homogeneous and isotropic cosmos. Yet, when studied in exquisite detail by missions like COBE, WMAP, and Planck, the CMB reveals tiny temperature fluctuations, satrapies that encode a wealth of information about the universe's early conditions and its subsequent evolution. These anisotropies are incredibly subtle, with temperature variations on the order of microkelvin, 1 part in 100,000, but they represent the seeds of all structure, the slight over and under densities that gravity later amplified into galaxies, clusters, and cosmic filaments. Scientists have extensively analyzed these anisotropies to test fundamental cosmological models, including whether the universe exhibits any preferred direction or central point. The dominant pattern observed in the CMB is consistent with statistical isotropy, meaning, on average, the fluctuations look the same regardless of direction. This strongly supports the cosmological principle and argues against any unique center or edge. However, some intriguing anomalies have sparked debate. For example, the so-called CMB cold spot is a region larger than expected where the temperature dips anomalously. Others note alignments of certain multipole moments, the so-called axis of evil, suggesting a possible preferred direction in the universe. These features have prompted intense scrutiny and various hypotheses, ranging from the influence of large cosmic voids to exotic physics beyond the standard model. Yet, none of these anomalies has achieved consensus as definitive evidence against isotropy or homogeneity. Many could be statistical flukes or artifacts of data processing. Crucially, even if these anomalies point to subtle deviations from perfect uniformity, they do not establish the existence of a cosmic center in any absolute sense. Instead, they may reflect local variations or complex early universe physics without violating the fundamental lack of a preferred spatial origin. Furthermore, inflationary theory, postulating a rapid, exponential expansion shortly after the Big Bang, explains the large-scale uniformity and the origin of tiny fluctuations, providing a framework in which no center exists. The CMB remains a cornerstone of observational cosmology. Its patterns help refine parameters like the universe's age, composition, and curvature, but consistently affirm a cosmos without a spatial center. In the next section, we will explore the concept of cosmic horizons and how limits on information shape our understanding of the universe's structure and centrality. The universe is vast beyond comprehension, but our access to it is fundamentally limited by cosmic horizons, boundaries beyond which information cannot reach us due to the finite speed of light and the expansion of space. There are several types of horizons in cosmology, each shaping what we can observe and how we interpret the cosmos. The most familiar is the particle horizon, which marks the maximum distance from which light has traveled to us since the beginning of the universe. It defines the observable universe sphere, centered on the observer, containing all events that could have influenced us. Another important boundary is the event horizon, a limit beyond which events will never be observable, even in the infinite future, because the expansion of space outpaces the speed at which light or information can travel toward us. These horizons mean that our view of the cosmos is always partial and dependent on our location in space-time. Each observer, no matter where, experiences their own observable universe centered on themselves. This subjective centering is a profound aspect of relativity and cosmology. It means that the center of the universe is, in a sense, wherever you are. The existence of horizons also implies that causality and information flow are limited. We cannot know or be influenced by events beyond our horizons, so any attempt to identify a universal center is constrained by these fundamental limits. Moreover, horizons highlight the dynamic nature of the cosmos. As the universe expands, some regions recede beyond our event horizon, disappearing forever from our view. This ongoing process shapes the observable universe's structure and our understanding of cosmic centrality. The interplay between horizons, expansion, and gravity defines the cosmic stage on which galaxies form and evolve. While local clusters interact gravitationally, the vast majority of space grows emptier as galaxies accelerate away from one another. Driven by dark energy, this picture challenges intuitive notions of a fixed center or edge. Instead, it reveals a universe where every point is a center of its own observable domain. Yet none is privileged over others. Understanding cosmic horizons reshapes our perspective on existence. It emphasizes relativity, locality, and the limits of knowledge, inviting humility and wonder in the face of the unknown. In the final section, we will synthesize the insights from our exploration to answer based on current knowledge and theory whether the universe has a center and what that means for our place within it. After exploring the vastness of cosmological theory, observation, and philosophy, we arrive at a profound and humbling conclusion. According to current understanding, the universe does not possess a spatial center. Our journey has revealed that the universe is, on the largest scales, homogeneous and isotropic, expanding uniformly in every direction. The cosmological principle, supported by observations of the cosmic microwave background, galaxy distributions, and large-scale structure, denies any privileged point or location. Gravity shapes local structure, but does not aggregate matter toward a universal center. Dark energy propels expansion, accelerating the growth of space and precluding collapse into any central point. The observable universe is a finite sphere centered on each observer, but this centrality is subjective, dependent on perspective rather than an absolute cosmic position. Even the deepest insights of modern physics, from relativity's coordinate freedoms to quantum gravity's emergent spacetimes, suggest that the notion of a center may not be physically meaningful. Instead, it may be a product of human intuition, a relic of our desire to find origin and place in an infinite, dynamic cosmos. Philosophically, this challenges us to reimagine our role in the universe. No longer the cosmic center, we become participants in a vast, interconnected web of existence, where meaning is derived not from centrality, but from connection, exploration, and understanding our limitations in observation, bound by cosmic horizons. Remind us that knowledge is always partial and evolving. Future discoveries may reshape this picture, but for now, the universe's lack of a center is one of its most profound and elegant truths. Embracing this perspective enriches both science and spirit. It invites awe and curiosity, a recognition of the cosmos as an endless frontier without bounds or centers, an eternal stage, where every point is as central as any other. And so, the question, "Is there a center of the universe?" leads us not to a point in space, but to a deeper appreciation of the cosmos and our place within it.